All right, I see it's just after 9 a.m. and I think we'll go ahead and get started. Welcome everyone to our distinguished lecture series. My name's Jeff McDonald, and I want to welcome you and all the folks both online and in person. This is also our 990 seminar series credit for our Masters of Water Security students. So welcome all of you as well. Before we get started, I want to acknowledge that we're gathering here or coming to you, streaming to you from Treaty 6 territory, homeland of the Métis, and we at the Global Institute for Water Security pay our respects to these First Nations and Métis ancestors of this place and reaffirm our relationship with them as we work with our various projects to address First Nations water issues. I want to thank the Global Institute for Water Security and Global Water Futures for underwriting and supporting this seminar series, now in its 10th year, as we learned last week. Don't forget that next week we have Deborah McGregor from York University, and she'll be talking about decolonizing water relationships. So I encourage you to participate in that lecture. But today, I'm very happy to introduce our speaker, Josh Larsen. Josh is a senior lecturer at the University of Birmingham in the UK in the School of Geography, Earth and Environmental Sciences. He's been there since 2018, and before that, he was a senior scientist at the University of Lausanne at the Institute for Earth System Dynamics. Josh completed his PhD in 2012 at the University of Wollongong in Australia, so that's where he hails from originally, as you'll quickly see when he starts to speak. And Josh has really made some deep impacts in the area of ecohydrology and biogeochemistry, and his interests relate to how water and nutrients are partitioned in the landscape and in ecosystems. Josh has received several accolades for his work, including an Editor's Award for Editorial Excellence from the Journal of Hydrology, and he's an associate editor with the Journal of Hydrology, or was from the period of 2015 to 2019. Anyway, it's a real thrill to welcome Josh, and I'm really looking forward to your talk. And without further ado, I'll turn it over to you now.
Well, thanks, Jeff, for the kind words and your interesting pronunciation of Wollongong. I'll honor that you took such great pains to say it. It's a hard word to say. So anyway, no more Australian names, hopefully, in this talk. And thank you very much for having me here. It's a great pleasure to be with you and throughout the internet and wherever you are in person as well. I didn't want the title to be too presumptuous. New thoughts on old problems. I just wanted a way to say that I'm going to talk about a few different things, and I hope that there's something for everyone in those parts that I'm going to talk about. So I'm going to talk a bit about snow to begin with, then I'm going to move to forests and water resources, and then I'm going to move to ecosystem engineers and an animal that you're perhaps quite familiar with in Canada called a beaver. So we'll see how we go, and hopefully some of it stirs your interest. So if I start with snow to begin with, what's the issue that we're concerned with in snow and that we're trying to tackle? Snow is just an integral part of the energy and water balances of the Earth as it ebbs and wanes, waxes and wanes over the Northern Hemisphere during the winter months. It's changing the albedo of that surface. It's having a big impact on the climate system. But in terms of hydrology and water resources, it's also locking up a lot of water as solid ice, and it's delaying its release into the hydrological cycle until the melt season. So it has a big impact on water and energy balances across the Northern Hemisphere in particular. However, it's undergoing rapid changes. I'm sure you've all seen lots of stories, lots of scientific papers, lots of news articles as well, and a lot of it's focused on glaciers, but perhaps also on snow, that this snow landscape, this snow climates and conditions are changing quite a lot throughout the Northern Hemisphere. However, there's so many different environments in which you find snow and which snow is occurring, and we don't really have a really nice complete picture of how they're all kind of changing. Are they changing the same? Are they changing the same way? Are they having the same drivers of change? It's quite a limited picture at the moment in terms of how climate responses or climate changes are impacting the snow that we have and the water resources that we might derive from those. So the kinds of things that I want to talk about at the beginning here on snow are really about whether or not we're expecting the snow melt, the snow that we've had accumulate over the winter season, whether that melt is going to be faster or slower as we move forward in this warming climate. You may have seen some very interesting papers on this that have shown through data primarily from the Western US that indeed we do see that in many of those places, snow seems to be getting, snow melt seems to be trending to be slower over time. And this has been attributed to the fact that the onset of snowmelt is occurring earlier in the warmer world. And because that early in the season has less energy and we're melting towards a similar endpoint of the season, the overall rate is slower. I'll show something, a graph to highlight that to make it a bit easier. But I also wanted to highlight in that figure on the left that this data that you see on that map of the Western US is from this big collection of this big snow monitoring network called SNOWTEL. And the vast majority of research that we conduct and that we see published on long-term changes to snow is coming from this SNOWTEL network. So it's a very Western US perspective on how snow might be changing. And that's simply because the US has been so good at setting up, establishing, and making that rich record of data available. And it's just there's nothing comparable anywhere else. And when I talk about snow, I'm also talking about not really the depth so much. What I'm really interested in is the amount of water held in that snow. So snow water equivalent, which is the amount of water that you would have if you were able to, the depth of water you would have if you were able to melt a column of snow. And when we have measurements of snow water equivalent, we can plot them over the course of the snow season. And this gives us these snow water equivalent. We can use an acronym as just SWE, and we get these SWE curves, which show that season. And you see that it has an accumulation season, which is where, of course, you can have some melt events in that season, but it's on average or on net, it's accumulating snow. You reach a peak, your peak amount of snow that you're going to have, and then you transition to a melt season, which is typically far shorter. Of course, you can have some accumulation in the melt season as well, but again, it's just dominated by mostly snow melt. So what do we mean by faster or slower snow melt? If we look at these, this is some data from one of the SNOWTEL stations, and you can see it's plotting data from the 90s, the 2000s, and 2010s. We're looking at these SWE curves. And you can see if we just focus on the melt season, so from the peak SWE down to the end of the season, under colder conditions, so going back further into the 90s, we had a higher peak SWE and a faster melt rate in comparison to moving into the 2010s. Things are a bit warmer. We've got less total snow. We're having that onset of snow melt earlier in the year, and so the slope is gentler. So we have a slower snow melt. So that's the broad picture of what we know or we think is happening so far. But again, because it's a very Western US perspective, one of my PhD students, Adria, decided he was going to try and pull together something that would give us a whole Northern Hemisphere perspective on what might be going on. So he's worked in earnest to compile these massive data sets. He's got about 10,000 sites of snow depth from across the Northern Hemispheres. There's only one. These have enormous variation in the length of the series available. They're all daily time steps, but they could vary from 1 year of complete data to 72 years of complete data. And he's also compiled data on snow water equivalent that's available outside the Western US as well, and put all those together using a model called Delta Snow, which has been previously published, to convert that snow depth data, which we have a lot of, to snow water equivalent. which we don't have very much of at all. Of course, there's some uncertainties in that, and Ardrey is soon to submit his paper on this data set that will be made publicly available, with all the nuts and bolts of how to, how that conversion between depth and snow water equivalent works, particularly with the two density parameters that are really important, using some regional climate information so that it's and it works quite well. So it's got quite good performance in the timing and the magnitude of those snow water equivalent curves. So if we use that data now, looking at this across the whole of the northern hemisphere, what do we see if we now take only data that we have long-term information on, and in this case from 1979 to 2021, and we ask, well, let's just take those melt seasons and ask, are we getting slower or faster? Is this consistent with what we would expect in a warmer world, to get slower or not? And the answer, as you can see, if we just plot this spatially across the northern hemisphere, is it's highly variable. It depends a lot where you look. There are some areas that have some clusters in parts of Scandinavia, for example. Parts between the Canada and the US also appear to be, have some regional consistency. But if you look at any region, you will also find lots of variation within it. So some places are getting slower, definitely, but a lot are getting faster as well. So the question is here, well, what's going on? We have a lot of areas that are getting faster, some are getting slower. We've got some that are not, perhaps not changing very much at all. Is this capturing what's causing this amazing amount of variation in terms of melt rates? So we've started to have a look in a bit more detail at this. And I think the important thing to highlight is that the melt rate, the rate at which snow is melting, is composed of two factors. It's how much snow we have to melt. So that's from that peak SWE, the peak snow water equivalent in those curves that I showed earlier, and the amount of time that you have to melt that snow. And although they sound very simple and straightforward, when you decompose the melt rate into those two components, you see two very different pictures in terms of what's happening to control the overall melt rate. So we see that we have areas that are having more snow in time, trending towards more and more and more snow that's being developed as snowpack, snow water equivalent, and areas that are getting less and less and less snow over time. They're not necessarily the same areas that they're not necessarily having consistent changes with the amount of time to melt that snow either. They could be two different things. So some areas that seem regionally consistent in Western Scandinavia in terms of really having a strong decrease in amount of snow that they're getting, can have some consistency in terms of melt days, but a lot of them don't. Eastern Scandinavia, for example, really shows an increase in the amount of time they have to melt that snow. So, and as you can see, as you go across Siberia as well, that you're getting quite a strong increase in the amount of time to melt that snow. So quite an interesting contrast when you decompose that melt rate, what's controlling melt, the amount of snow and the time that you have to melt it. That's driving these changes. And I thought I would just highlight a local example from where you are in Saskatoon. Adria just created this for me the other day. This is snow depth information from Saskatoon that's been converted to snow water equivalent using the model. And this is a good example that shows, why things are so complicated. So the total snow melt is decreasing, but also the number of melt days is also decreasing. So everything's kind of decreasing at once, but the total snow that's available to melt is decreasing faster than the time to melt. So the overall impact is a slower melt rate, but it's important to note it's far from a constant melt period. So the melt rate is decreasing, but it's not in the same period of time. That's also decreasing. So we've got these lots of contrasting effects here that conspire together to cause an overall trend in melt rate. So I guess if I was going to give you a take-home message from the snow melt work so far, it is that yes, of course, we have many areas across the Northern Hemisphere that have slower melt, that are melting slower in time, but there are many areas, just as many, if not more areas, that are melting faster as well with time. Now, the question is, what's driving these effects? There's certainly, we're still in the process of decomposing that in a bit more detail. So some of these will be purely temperature-related effects that are affecting the melt rate, as well as whether you're getting rain versus snow in the first place. That's going to accumulate the snowpack. And some of it will be purely precipitation effects. So even though it's cold enough to cause snow, if it was available, they're just not the weather systems responsible for the delivery of precipitation are just not bringing as much precipitation as they used to. So there's those two factors that we're currently looking at to get into those drivers in a bit more detail. But just out of interest, if we look at the graph on the right, where we've plotted the x-axis, which is these trends in the snow melt, the amount of snow that we have to melt, and the y-axis is the amount of time that we have to melt. So there's two components that come together to make melt rate. And we've plotted this against the average peak snow water equivalent, the average amount of peak amount of snow that we have to melt from those stations. It's a lot of these areas that are having slower melt are really these quite deep snowpacks that are having these trends towards lower, but they're shallowing trends. So they are deep snowpacks, but they can have quite strong shallowing trends, and they're the ones that are really starting to dominate those areas with slower melt. So why is any of this important? Why would you be interested in all these sort of arcane ideas on and analyses on snow melt, the rate of snow melt, whether or not snow melt rates are changing? The rate at which snow melt is entering the landscape has a big impact on aquatic ecosystems downstream, has a big impact on recharge rates going into the subsurface storages that are super critical for later season flow substance, so going into late summer and winter as well, when we don't have much snowmelt during winter, obviously, but we need some subsurface storages to supply streams. So it has a big impact on recharge, has a big impact on the seasonality of that stream flow and the dynamics of that seasonal stream flow. And of course, if we're melting snow faster, perhaps that cover's also changing. And so we're having less areas covered with snow and more with vegetation. So we're changing those relationships with ET, evaporation to the atmosphere as well. So all of this has pretty big implications for the aquatic ecosystems, but also our planning and our water infrastructure that we have downstream, as the amount of snow that we have and the rate at which it's entering that system is changing. So I'll take, that was snow. I'll move now to those that might be interested in forests. So the relationship between trees, the water that they use, and the water resources that we have. What's the problem? The problem is that much of the Earth's surface has undergone or is undergoing some kind of change. Perhaps due to climate, but and to a large extent due to the work of humans. So we are clearing areas for agriculture, we are changing landscapes for forest use of various kinds. And as we change those landscapes and change the vegetation, either we remove it completely or change the vegetation to something else, we change that amount of water going back to the atmosphere in some way. And as we do that, we change the amount of water as a result that might be available as a resource going to our rivers that could be available downstream. So a very simple question is, what are the implications of land use change? And remember, much of this is transient. There's very few areas of the earth that are in some transition between steady states, if you like. What's the implications of this land use change for those water resources? This is a very, very old question. Lots of people have been looking at this from very interesting perspectives for a very, very long time. I want to look at just one component of that, which is also got a very long and rich history of analysis and study, which is the paired catchment approach. If you haven't seen this before, it's quite elegant and quite simple. The idea is that you have two catchments. One will be your treatment catchment. That means you're going to do something to it. And what I'm going to talk about, what we're going to do is cut all the trees down. So the treatment catchment, we cut all the trees down at some point, and then we either let the catchment regrow naturally, or we help it in some way, or we might add a plantation of trees that we're interested in, for example. The other catchment is a control, and this is a catchment we don't do anything to. The idea is that these two catchments are very similar. They're very close together. And they are similar in almost all ways, except for the fact that we're going to cut the trees down in one and not the other. What's the issue here? The issue, I guess, it's not a deep criticism. It's just a result of the process of doing science, in that everyone wants to come up with new ways, obviously, to try and analyze this relationship between the treated catchment and the control catchment. But as a result, there's not really a consistent method of comparison between a treatment and a control catchment. This could be a statistical comparison. We could use linear regressions. We could use fuzzy logics. All sorts of approaches have been taken that have been very interesting to try and compare these. We could use water balance methods that assume some kind of steady state, their transition between some steady states, which could be these Bodico type approaches or Zhang curves, as they're often called, or they could be model-based. Someone might be building a model, a hydrological model around those catchments and using that to help interrogate the differences between the treatment and the control catchment. In any case, the basic question hypothesis is usually the same, and this is something we've been asking for a very long time in hydrology. It's whether or not we do see this increase. You know, if we do cut down trees, we reduce evaporation, we should increase discharge. Is that the case? And does it recover as that vegetation regoes? Does that increase in discharge decline again back to the pre-treated condition? And a lot of time and effort has been spent looking at this. And I think one thing I would say to summarize it all is that it's very complicated. A lot of the results show huge variation in responses and in terms of explanatory processes or explanatory drivers for what might be causing those differences, or causing that variation, I should say. So if we look at the graph on the left, this is from a well-known synthesis. And again, the trouble with syntheses is that you're taking all these comparisons of differences between between a treated and a controlled catchment that may have many different methods used to analyze those differences. So part of the reason for the variation can be simply due to the large variety of methods that we've used. If we look at the graph on the left, this is from one of these syntheses in 2005, and it's looking at what's happening to that water yield as a function of rainfall, so as a runoff fraction, so how much rainfall is being converted to runoff. After we've cut down the trees, yes, runoff is going up. That's great. That's conforming with what we expect. Is it coming back down? Well, in one case, yes. In another case, maybe, but then it goes back again. In the other case, not at all. But look how inconsistent those patterns are as well, how variable they are. If we try to look at what might be controlling increases in the variety of responses that we see in the increase in water yield after we cut down trees, one way to do that is on the right, which is to compare with the amount of forest that we've harvested as a fraction of the area. So Have we cut down 60% of the catchment? Have we cut down 100% of the catchment? And the result is not easy to pick. You know, it's, of course, you may see an envelope there on the right, but you don't see any sort of confident relationship that you'd want to stake your career on. So the answers have been variable and complicated so far. So what have we trying to do? So we've had lots of students trying to compile data, time series data from all these paired catchments. So by time series, I mean getting the annual time series of discharge and rainfall. And from that, we get this ratio, this runoff ratio. So discharge or runoff divided by precipitation. So how much precipitation is being converted to runoff. The reason we do that is because we want to control for precipitation effects. We want to, you know, if the catchments receive slightly different rainfall, or if in a wet year, dry year, we want to control for that effect on the runoff. So that's the data that we take. And the approach that we take here is something borrowed from economics. It's called difference in differences. And this sounds like a bizarre term. It's probably something you never heard of. So let me give you a quick example. The people that were largely responsible for helping to develop this method in economics just won the Nobel Prize last year. And the original study that they did this with had to do with minimum wage rises, or minimum wage, and whether or not this question of whether or not increasing the minimum wage in the United States has an impact on employment. Does raising the minimum wage, for example, cause employment rates to go down? So what they did is they said, well, let's try and come up with a natural experiment. So they took two states that are very close together, New Jersey and Pennsylvania. And one state, I can't remember which one, I think it was New Jersey, was raising the minimum wage. And the other one, Pennsylvania, was not. So they said, well, let's see if we can track this effect of the minimum wage by comparing the two. So the difference is you take the two states as two spatially different entities, but you also take the time periods before the minimum wage rise has taken place. So they're already going to be different anyway, of course, beforehand. They're not going to be identical. And then you take the time period after you have the minimum wage and the difference between those. So you're saying, well, if I control for the fact that they were going to have differences anyway, but I would expect the trajectory to be similar on the control case. So in the case of Pennsylvania, I would expect New Jersey to behave like Pennsylvania if they didn't increase the minimum wage. And they came up with a result that was, I think, that actually employment went up or something. But anyway, it has a natural application to paired catchments and hydrology, because what we can do is take, if you see this plot here, which has got this control catchment in green and the treated catchment, the catchment where we're cutting trees down in blue on the left. And we take the data before we cut the trees down from both the treatment and the control. And we can construct a table on the right here to highlight the basics of what's going on. And then I take just an example, which is I take the average of the 5 years after the trees have been cut down in both the treated and the control. So I take the difference between those, and then I take the difference in the time, and I take the difference between the catchments, hence the name difference in differences. And in this example, I find that the treated catchment has 6% greater runoff than we would expect based on the pre-treated, the pre-treatment trends or the pre-treatment conditions. Mathematically, this all collapses to an ordinary least squares equations, which are quite nice to handle if you're interested in the details. But the idea is that by doing all of this, what we really want to do is try to boil things down to one number. So what we're going to do is we're going to take it the simplest approach possible, which is where we take as much pre-treatment data as we have, so as much baseline data as we can get, and use that as this pre-treatment condition, however long that period is. And then we're going to take compare that with the post-treatment time series. So after we cut the trees down, we're going to compare it to the first year, the second year, the average of the next 2 years, the average of the next 3 years, the average of the next 4 years, and so on and so on and so on. And this is a plot of what you get when you do that. So on the y-axis is this difference in runoff. So this is basically saying we're getting in the same catchment that I showed before. So this is the results from the time series I showed in this graph. So the time series in the graph on the left. If we can see that in the first year, we're getting about a 15% increase in runoff than we would otherwise expect based on the pre-treatment conditions. And then you can see it conforms to this nice exponential decay afterwards. And the nice thing about having exponential decay is that we are able to try and extract or distill things down to a single number. And this single number is a characteristic time scale, which is that tau symbol there of 5.3 years. It's sometimes called an E-folding time scale, which basically means in this case that it would take 5.3 years for the runoff to decline by a factor of E. So it's not the time it takes to reach, to go back to pre-treatment conditions. It's the time it would take for runoff to decline by a factor of E, which is 2.17, or don't test me on E. So how much of runoff change would we expect due to land use change, or due to this cutting? In the simplest case here, just cutting the trees down. Of course, it depends when you ask, and a lot of people have highlighted that already. But I think with this approach, you can really the nice thing is that you can see the importance of, or at least in this example, of the initial changes and its decay back to pre-treatment conditions, and the ability to take a single number from that of a characteristic timescale. Does it help in any way? Like, is this at all useful? So let's go back to this plot I showed earlier, and I'll just highlight this one result from this one catchment that is highlighted in red there. So this one that goes up initially, and then it goes up and down a little bit, and then it comes back down again after 10 years. Let's take that catchment. And so that's the kind of result we would have got previously from a paired catchment analysis. And let's take it with this difference in differences approach. So this is the time series on the top between treatment and control, treatment year. And if we do the same approach, comparing year on year, the average changes, we see that, again, we get this nice exponential decay, about 18% increase in runoff in the first year, and then that's declining over time again. But you can see it's a much shallower decline in this case, so it's about 12.2 years for that runoff to decline by a factor of E. Both of those catchments, incidentally, are Australian catchments, and I didn't want to give you the impression that I only study Australian catchments, or that, and of course, it has a particular kind of climate. The runoff ratios in total are quite low. So is this just a peculiar feature? Does it work for other catchments? So I'll show another example from the Andrews Forest, which has much higher runoff ratio, very different climate, lots of snow, seasonal snow as well, and a well-studied catchment that I'm sure many of you would be familiar with. And again, the time series on the left of treatment and control, and then the same method of analysis of seeing how these differences propagate in time. About 12 to 13% increase in runoff in the initial stages, and then very, very, very slow decay over time. And in fact, so slow that it's giving a characteristic timescale of 53 years. So 53 years for this runoff to decline by a factor of E towards pre-treatment conditions. And in fact, of course, that's slightly unrealistic in the sense that, of course, after 53 years, perhaps there's been a mean shift in the climate anyway. So this is not to say that it's going to definitely take a very long time to get back to pre-treatment conditions. you should take as an indication that it's just very long response times in general. And of course, it may never go back to pre-treatment conditions because the new climate itself has perhaps shifted slightly in its own average conditions. It's just an indication of the response time of the system. So if we do that, we're still compiling all that for many catchments around the world. The students have collected vast data sets. And there's this huge variation in these characteristic timescales or response times. These initial increases, somewhere between 10 to 16%, is quite typical for most catchments around the world in terms of the extra runoff that you get, but high variation in that timescale that it might take to recover back to pre-treatment conditions. And that's a function of many factors. It's a function of the vegetation that's coming back, so the regrowth, or perhaps the forest that's being planted there. It's a function of the catchment dynamics as well, how much storage it has. I don't think it's very much a function of the area of catchment that we deforest. This is not a powerful explanation of these dynamics. It's much more about the size of the trees, how fast they grow, their partitioning as they grow between ET and growth, which changes in many parts of the world, depending on the vegetation and depending on the climate. And so it has a strong climate dependence as well. So I hope that I give you the impression that it is possible to make some progress on distilling and simplifying some of the enormous variability and variation in dynamics of runoff or water resource responses to land use change. Of course, we're taking a very simple example of land use change, the simplest possible, in fact, where we cut everything down and then let it regrow. Many areas are much more complicated than that, obviously. So, but if we could try to get boil things down to a simple explanation for the simplest case, I think we'll be in a better position to tackle more complicated cases as well. And I think these decadal scales of hydrological change are really important because they're kind of stuck in what I call this representation trap in terms of modeling. We have daily hydrological or models that work on daily or sub-daily time steps, really used for hydrograph prediction, that don't have any of the sort of growth dynamics of vegetation that would be important in sort of explaining some of these decadal changes. And they're certainly too short for some of the steady state model assumptions that might be from a Bodico or a Zhang curve perspective, where we're assuming things have transited completely between two steady states, when I think clearly, we're studying cases over a decade or more or multiple decades where they're in that transition between steady states. Okay, so finally, I'll just quickly try to end on ecosystem engineers. So we're going to switch gears now. We're not going to have whole catchments. We're going to have river reaches. So we're going to have a section of a river. And the interesting thing about beavers as an ecosystem engineer, of course, is that they, as the name implies, they can do a lot to the river landscape. So that photo I'm showing is a dam that is valley spanning in a case in Germany. So there is no river anymore. The dam spans the entire valley, traps all the water, and then there's the next dam after that, and the next dam after that, and the next dam after that. So quite profound changes to what it was before, where it was really just a drainage ditch. So as a result of these changes, this engineering, if you like, the beavers have, they're changing the local hydrology of the system, the river reach scale hydrology, but they're also changing the way that nutrients are cycled and the ecosystems that will take advantage of them and the ecosystems that will be that will live there. We also face many issues in terms of water quality. There's many challenges in terms of excess nutrients in river systems, from point sources to diffuse sources from agriculture, for example, to point sources from wastewater treatment plants and so on. And the question, there's always this question about, can we have nature-based solutions that might be able to help? There are many words synonymous with that, but I'm sure you've heard something along those lines of, nature-based solutions. Are there things that we could do to help that along, to help solve some of these water quality issues? So my question will also be, well, are beavers a good candidate for that or not? So if you're interested in the nuts and some of the, if you're interested in excessive detail of hydrological changes, water quality changes, biogeochemical changes, and ecosystem changes that beavers can create in river systems, then I would certainly encourage you to read our review that is just far too long. So it'll read with don't say I didn't warn you in any case. I think we published last year. The hydrological changes are local, so they're building a dam in the river system. That dam stores water, it has implications for the groundwater system around it and so on. It's releasing that water slowly. It creates a pond, it can create wetlands. But the interesting thing about that is that it creates ponds, it creates areas of slow flowing or still water that never would exist in that river system otherwise. So it's creating an area that can create, pond, wetland, lake-like conditions. Vegetation can grow there, littoral zone vegetation, emergent macrophytes. You can get a lot of lateral hydrological connectivity, a lot of water exchange between the channel, the pond, the wetlands laterally. And you get this disconnection longitudinally because that dam is there slowing that water flow going downstream. You also get large differences just depending on the landscape that you're in. Steeper landscapes get hot dams, might have less floodplain areas, so they might not have much room for wetlands and so on. So there's this huge landscape context as well as to how the beavers might impact the hydrology and the ecosystems that go within it. But they do, by creating that by decreasing that longitudinal connectivity, they create space for very still water anaerobic conditions in river systems that otherwise would not exist. Now, in our review, we kind of, as you tend to do, try to come up with what we know so far in terms of their impacts. So I just wanted to highlight here the dissolved organic carbon, the DOC in A, and the nitrate, NO3 there, minus in B. So as you can see, there's not a lot of studies there, but they tend to show, yes, we're getting mostly decreasing. We mostly seem to have DOC increase if we go downstream. And what I mean by increase is that if you go from upstream to downstream of the beaver system, you found that concentration was increasing. In contrast, I should say, for nitrate, we see that, it seems to be that they're finding a decrease. Now, those numbers aren't large, but there is this question, well, does it hold if we start to sample beaver dams everywhere, or if beavers start to, what are we really going to expect? Is this going to be consistent? Is it going to hold? What's the variation going to be like? So we have this, I just wanted to highlight one study that we're conducting and some new results from that, which is a big project in Switzerland that a few students and colleagues and employees are undertaking. About 130 beaver dams across Switzerland. This is a subset of their kind of a real citizen science campaign, which is every 5 years or so to survey the beaver dams across Switzerland. And this time they also took some water quality samples in some of those for us. So they're taking samples upstream of the beaver system. So it could be one dam, it could be 5, it could be 20 dams upstream of that, and then downstream of however many beaver dams you have in that reach. So upstream and downstream. And I'm going to show a couple of graphs where we're looking at the relative change in that concentration. So I'm asking, how does that concentration change going from upstream to downstream through that beaver system? Are you losing carbon or nitrate, or are you gaining carbon or nitrate as you move through? And we're going to do it temporally as well. So we did this survey in winter and we did it in summer, trying to get this temporal aspect to it as well, to get a seasonal impacts on these changes. So we get a bit of a scatter plot here. So what I'm showing here is this relative change in first nitrate. So we have winter, relative change in winter. Are we adding nitrate or are we losing nitrate? So negative numbers means we're losing nitrate. Positive numbers means we're gaining nitrate in winter, and on the y-axis, the same on summer. And I've divided this into, we've divided this into 6 categories of responses, basically. So you have I won't go through all the responses there, but all the options depend on whether you're gaining or losing and whether that is greater or less in summer or winter. So what it boils down to, though, is this pie chart here where we have category 1 and 6, which is summer losses are greater than the winter losses. So we're losing more nitrate going downstream in summer than we are in winter. And 6, which is where we're switching. In winter, we're gaining nitrate going downstream to some extent, and in summer, it switches to losing nitrate. So those 2 cases explain the majority of the data set so far. So nitrate is decreasing in a majority of cases as we go downstream in beaver dams, and it's mostly doing so in summer. And as we have some sites where we have higher resolution temporal information, you can see the seasonal dynamics much clearly. But it's just really cool to see some of that in a massive spatial snapshot across a whole country. And I think it also highlights, though, that it's not super straightforward. There is a huge variety in those responses as well. So we're currently looking at what's explaining some of this variety of responses. Is it the number of dams? Is it this landscape position? And all these other factors that the volume of water that's being held there. So some of the residence times is a big factor here for nitrate. If it's not holding it for very long, then it doesn't have a lot of time to have these anaerobic reactions like denitrification that are causing nitrate to be lost in the system. So we're currently looking into that, but a huge amount of variation there as well in nitrate responses. Much clearer in carbon to some extent. So what I would highlight here is that we're getting a much stronger summer signal. So a much more seasonally dominated signal in carbon. So what's happening here is in summer, we're putting a lot of extra carbon into that water going downstream. So water's flowing in, carbon was flowing in, carbon's flowing out of these beaver systems, and it's mostly increasing. So we're mostly getting more carbon as we flow through, and it's doing it much more so in summer than in winter. So why are beaver systems doing this? It's this anaerobic zone that allows a lot of these reactions and these transitions between, lentic and loading, so still and flowing water that happen in beaver systems that would never happen in a river system without the beavers. Creating these anaerobic conditions in terms of nitrate, we've got denitrification where we could lose the nitrate, but another student has been working on this and shows actually there's a lot of organic mineralization as well, which is actually increasing the ammonia concentration quite substantially. And that increase in ammonia being exported downstream that can reoxidize the nitrate, that may be one of the explanations behind this huge variation in nitrate responses or changes that we see in the beaver dam systems, with generation of ammonia and nitrate as well as its reduction in some cases. So that may be, we're getting more results on the ammonia that'll help clarify some of that in the future, but it's an interesting case. And the DOC is really driven, we're gaining carbon. So the idea that these beaver systems are pumping more carbon into the river system, into those downstream systems in DOC, really driven by that greater primary productivity that lentic and wetland pond zone allows when beavers build the dams and allow that water to be backed up behind in the ponds. All that still water with its emergent, submergent macrophytes, its grasses and everything, all of that extra primary productivity is contributing so much extra carbon that it's going into the sediments and all that extra, and that in turn is able to be exported downstream as high dissolved organic carbon concentrations. So just really profound changes, I think, that that are to some of these river systems, the cycling of nutrients in some of these river systems that would otherwise happen if beavers weren't there. And I think also the important thing is it's over very small spatial scales. So if you think about variation in nitrate and carbon in river systems without the beaver dams, of course they will evolve as you go downstream, but the scale of the changes are so much greater. The cycling is so much greater over such small distances when you have these beaver systems in there, because we're talking about tens of meters, hundreds of meters, and in some cases kilometers, a kilometer or more of a river reach in which these beavers are causing all these changes in nutrients, and that would just never occur. So the cycling of nutrients is changing profoundly as a result. And also the ecosystems, because we have these still water habitats, flowing water habitats in between, and just all these transitions that occur in between. Why is any of that important? I mean, it boils down to this idea: what on earth do you think is natural? River restoration is a billion-dollar industry around the world. Everyone has different ideas about what that river system should look like and what ecosystems it should sustain, and what a healthy ecosystem would look like. The important point is that if you've got beavers in there, it's probably going to look very different to what you otherwise thought it would look like, both not as much hydrologically, but certainly in terms of water quality, in terms of nutrient cycling, in terms of ecosystem dynamics. They're all going to be very, very, very different under beaver impacts than if you don't have them there. And so that's something we have to grapple with, and it's something we have to grapple with whether we like it or not, because beaver populations are expanding greatly in the UK. They've had a reintroduction. So in the next 50 years across Europe, the Eurasian beaver, across many parts of Western Europe and Eastern Europe, across the UK, and of course the Canadian beaver, and moving across many areas of the USA, southern USA, where they were regionally extinct, they're moving back into those habitats now. So whether you like it or not, they're going to be there doing these things. So it's just such an important issue to grapple with. How are they going to change the water quality? How are they going to change the ecosystems in those areas? And with that, I think I will leave it there. I hope everyone got something out of that, and more than enough for you to think about. And thanks to all the many people and students and collaborators that help contribute to some of these studies that I showed today.
Great, Josh. Thank you very much. Always a clear and entertaining talk. So thanks very much. And of course, the beaver issue, even along the banks of the South Saskatchewan River in Saskatoon, is very apparent as trees are being lost at a almost weekly rate, it seems, as you walk along the river. Okay, so we'll open it up. We've got a few minutes for questions. I see John had typed a few into the chat. John, you might want to unmute and ask one or two of those, perhaps, or anyone in the room. I'll moderate perhaps the chat, and I think Kim is in the room and she can moderate any questions from the live audience. Over to you, John.
Yeah, Josh, just a question. Were you able to separate out in your data set where you looked at acceleration or deceleration of melt rates, were you able to separate it out from areas where snowmelt is currently before the summer solstice versus those where it's typically during or after the summer solstice? Because with warming, you get very different results because of the changes in insulation as you move closer or further away from that period of time.
No, we haven't done that yet. That's a good point. I mean, yeah, definitely. Yeah, I agree. Definitely the amount of energy, so the amount of incoming radiation is critical as well, for sure. But I think that's a very nice way to look at it. If we looked at the solstice, that would be a good way to kind of simplify the analysis, because obviously the incoming radiation data can be otherwise it can be difficult to estimate. So actually, that's a good point. Yeah, we haven't looked at that though. We have looked at, I guess we've looked at, snow climate kind of effects. So we've tried to simplify with indices whether you've got winter being half the year or not, and whether it's rapidly approaching 0 degrees or whether you hang around 0 degrees for a long time, for example.
Yeah.
So we've looked at some of that, but no, that's a good point. I'll write that down. The solstice is a good idea.
It's one thing. Yeah. Anyway, it helped us understand it better when we started looking at that.
Perfect. Thank you.
Thank you. That's and then the other one was very interesting on the. Well, lots of reasons interesting. Good talk, but lots of interest in the effects of forest disturbance on forest recovery. And of course, in Canada, we're experts at disturbing forests here, so it's of tremendous interest. And there are different results in different parts of the country. And I'm wondering if you've were able to distill down in anything like forest replanting, reforestation efforts, and the effectiveness of these. I mean, are we even moving back to that original forest cover in some of these places, or is that lost forever?
Yeah, many of them, as you know from those paired catchment studies, many of them are cases where they perhaps cleared a plantation originally, so it wasn't even a natural forest, and in some cases they've replanted with a plantation. So yeah, there's a lot of effects there. I would say that the percent cover definitely doesn't look like it's terribly helpful, and it's definitely coming down to the size of the trees. But unfortunately, that if we think about how tall they are, how old they are, and of course some of those trees having different biomasses, just having different water demands, having different water carbon allocation demands, and we just don't have the data. There's just if you have a paired catchment study, it does not come along with forest inventory information as well, unfortunately. Perhaps that of some in Canada that do. I mean, that would be perfect to drill into the details of that in some of those cases. You do have some information on species in some cases, or the broad range, what they've planted and what they've cut down. But really, we've got no further information on the forestry dynamics. We do get recovery for sure, but it's just, of course, it's not quite what you wanted, because you're going to have all this. It's going to take 100 years for succession to go through. So in Australia, for example, the succession with eucalypts, it takes a long time. You get pioneer vegetation initially if it's just natural regrowth, and it takes a long time for that canopy to return, even though that cover has returned. So you've got 100% cover, but you haven't got that succession to tall stand, high biomass.
Yes, and we find the roots take much longer as well, and that
sure, yeah, absolutely, yeah,
it's everything going on in the soils that is slow. So anyway,
yeah, absolutely.
Good,
Thank
thanks.
you.
Well, and just before I read a question from the chat, I guess that 53-year unfolding time, the H.J. Andrews, I wonder too if it could be logging road impacts. Tom Dunn did work in the 80s showing that when you have roads or not roads, that can really increase that length of time to quote unquote recovery. But
Cool.
let me go over to a question from our audience. Magali Nahemi, who's an assistant professor at Trent University. Josh, great talk. Thanks for sharing the new insights. I wonder if you found new trends or insights on the drivers of runoff response after forest removal by using the new approach to evaluate the data.
Well, thanks for congratulations on the new appointment, Magali, I should say. Great news for you. That's I'm glad it's always good to see people getting jobs and continuing research. Drivers of runoff response. I don't think so. No, I don't think we're going to get insights.
Yeah, I was just going to say, because there is all of this historical data, and I was wondering if by looking at a new method, you have got any new tips on the main drivers.
Well, I think
I know there's all those impacts we're discussing here, but yeah.
I think what it shows is that there is a convergence. So when you can simplify things down to these exponential decays, it shows there is a convergence, and it's just the time scale over which you expect that to occur is different. So there is a convergence, which is quite nice. So there is this kind of growth response, but it diverges massively in terms of length of time. Runoff drivers, I think, definitely because of that decay, you've got to invoke the subsurface responses as being critical there. So time to build up the biomass, the root systems, as John was saying, but also how that interacts with the soil and and the groundwater systems that are feeding the runoff. They're all involved in that. So I obviously I don't want to draw an unnecessary parallel with sort of hydrograph recessions, because I know that's what people have a lot of in mind when they think about response times. They're not at all the same, but they certainly this huge coupling with the subsurface system that drives this very slow recovery towards pre-treatment conditions.
Thank you.
Kim, are you there? Any questions from the floor in the room? I encourage anyone there or any students we have online to ask a question.
Nothing in here from the room
Okay.
just yet, Jeff, thanks.
Well, we're just over the hour, so I think we'll end here and thank Josh for a really clear and informative seminar. Thanks so much, Josh. And you'll see in the chat right at the very top, I put the Zoom address for an early career discussion that we're now going to have with Josh. So we're going to exit this call, and for those that are there live, they can go on to their computers, or those that are on Zoom can log off of this address and go on to the address that is listed in the chat. And yeah, please join us. And what we're going to do is have an informal discussion as we do each week, this time with Josh, and it'll be an opportunity to hear his perspectives on early career issues that some of you might be facing. So we'll take a 5-minute break and see you back on the new Zoom channel in 5 minutes. And Josh, thanks so much. Get a coffee, and we'll see you shortly.
Thanks very much, Jeff. Thanks, everyone.